What is so important about driving faster than anyone else?
Racing is important if you do it well. Racing, it's life. Anything that happens before or after, it's just waiting.
Dear ladies and gentlemen, dear partners, dear sponsors, dear Formula student community, family and friends. I want to welcome you to our 2022 rollout here at the event area at Sauber Motorsports here in Hinwil. I am honored to welcome you to this venue. My name is Jan Bernert and I'm the CEO of the AMZ Racing team. Tonight we present you our newest prototype of the Academic Motorsports Association in Zurich, on which our students worked hard under astonishing motivation and time pressure. We will start with an introduction to the general concepts and technical innovations before moving over to an outdoor demonstration on the parking next to the building. I'll introduce that later. For the very first time in the history of AMZ, we put up the challenge to bring back together two teams, the electric and the driverless one, and build one single car after having run two cars in parallel for the last 5 seasons. The new car will feature a full cockpit for the driver while offering all-around driverless capabilities as well. A car ready to race and to be raced. This adds up a whole new chapter of challenges. New trade-offs are to be found and more systems have to work together and fit into the car without compromise. On the other side, bringing two teams together seems easy, it's not. Different dynamics, various approaches to problem solving, distinct time plans between driverless and hardware, all require thoughtful planning to make everyone work together towards that common role of bringing the new car ready to race. There are benefits as well, of course. Rethinking routines, bringing in new ideas and tools, questions old practices, and sprouts new ideas of working. Finally, coming back to what we are here for today, I want to raise your attention to the presentation of our newest electric driverless prototype. Enjoy!
I want to start off this presentation with a very fundamental question. Why did we build Bernina? I think this question has been asked by our family and friends who haven't seen us in almost a year, or the sponsors and partners who receive unconventional requests from us at least once. And the answer is very simple. We want to build the most successful car in AMZ history. But AMZ does not only develop prototype race cars, it also transforms numerous inexperienced students into creative engineers. My name is Goranj. I am responsible for the inverter, and my colleague Ilya, he's responsible for the motor. We both want to present you the key highlights of this year's car. Bernina features the strongest, most powerful motors in AMZ history. To bring this power onto the racetrack, we need optimal traction, which was achieved by innovations in active aerodynamics. And AMZ would not be AMZ if we did not integrate our in-house developed mode-decoupled hydraulic suspension alongside a fully self-developed drivetrain. Before I get into more details, I want to tell a small anecdote about our manufacturing. As any good engineer would do, our chassis team did a great job of documenting their work in pictures. After long weeks of day and night shifts, we wanted to look back at the progress we made, when we noticed that the photos tag the locations where they are taken from. So on Thursday, the phone said that we worked from Dübendorf, our workshop. On Friday as well, as usual, we worked from our workshop in Dübendorf. And since we don't rest on weekends, we once again worked from Dübendorf on Saturdays. But on Sundays, the phone thought we were at home. Not only did our friends and family believe that we lived at the workshop, no, our phones realized that the workshop was our home. But only through that effort, we were able to build the newest car. It has a full CFPR monocoque, it is handmade, weighs only 25 kilograms, and does not compromise in torsional stiffness. This is achieved by a lightweight sandwich structure and an aluminum honeycomb core.
In the aerodynamics department, we innovated quite much this year. Not only did we build 3D end plates and a lightweight mounting solution, no, we also optimized the car for the so-called powered ground effect. So, in Formula Student, there's this running gag of people saying, wings don't work. Our aero department took that a bit too literally and started innovating with active aerodynamics. So, we decided to talk a bit more about this. To sum it up, we have two fans which are generating a vacuum-like zone under the car by accelerating the air to over 160 kilometers per hour. Two 4.5 kilowatt motors are bringing us an additional 150% of downforce. The biggest advantage of this system, though, is that we can generate downforce from standstill, and thus accelerate even faster and reduce lap time drastically. Our suspension module has built this year the 5th hydraulic suspension. It is fully self-developed. Therefore, it allows for freedom in packaging. We can place the spring dampers element anywhere in the car we want, so optimally somewhere low to lower the center of gravity. Furthermore, it allows for full mode decoupling. Heave, pitch, roll, and warp can be controlled separately without affecting each other. Therefore, we can guarantee optimal grip on all track conditions and once more reduce lap time.
Our electronics module faced many challenges this year. The chip shortage, worsened by lockdowns and the pandemic, meant that many components were not available anymore. They had to redesign and rethink every part of their work. The manufacturing of the PCBs and the reworking of the design would have been enough of a task, but they still had to wire all the sensors, actuators, and PCBs with over 200 meters of cable. And they still managed to stay innovative after that. I want to tell you about one key highlight of their work package, the Accumulator Management System, in short AMS. The AMS monitors cell voltages and cell temperatures to ensure a safe operating state of the accumulator. In the high voltage accumulator, the AMS is directly mounted onto the cells and communicates via infrared to decouple it from any noise. In contrast to that is the PGE AMS. It is made for a low voltage system which can handle high currents to ensure enough powers for the active aerodynamics. After telling you a little bit about the framework of the car, I would like to continue with the drivetrain. The first part of our attractive system is the accumulator. It is also the heaviest part of our car. It weighs roughly 40 kilograms and has a capacity of 6.3 kilowatt hours. We have to transform the direct current of the accumulator into alternating current. This is done in the fourth generation of our self-developed inverters, the i4s. They have a peak discharge power of 100 kilowatts for 5 seconds. We opted for a dual inverter system this year, meaning that each inverter powers one axle of the car. This allows us to have more packaging freedom and less design constraints. The inverters are not only very powerful, they also allow for a very precise control of the motors. This is achieved with a high switching frequency in our state-of-the-art silicon carbide semiconductor modules. The inverters communicate once again with optical fiber with the motors to decouple it from any noise. Ilya will tell you more about the motors now.
So yes, let's talk about the heart of our car, the motors. Bernina features our 11th generation self-developed motors, the so-called M11. With its 43 kilowatts, it's the strongest motor that AMZ has ever built. Furthermore, we are using snake-line magnets to reduce eddy currents in the rotors and therefore lower the temperature there. The mass of the motor is 2.5 kilograms and it reaches a speed of up to 28,000 RPMs. Our car features 4 of these motors in each wheel, which combined with the gearbox provide over 1,000 Newton meters of torque to the car. Our wheel packaging consists of 10-inch tires with self-made carbon fiber rims. This carbon fiber rim is then mounted onto the milled wheel hub, which has an integrated planetary gearbox. Our highlight, though, is most definitely the SLM-printed, topology-optimized upright. So topology optimization helps to reduce weight while preserving structural integrity. It is an aluminum structure which transfers the loads from the road into our chassis and suspension. Overall, the wheel packaging consists of many multifunctional, lightweight parts which help to reduce lap time once again. So, as any good project, we started off with a nice timeline like this. We started with the design phase, went on to a manufacturing phase, and afterwards to a testing phase. And in the end, finally, we aimed to go to the races from July to September. And really, everything from there worked perfectly, except that it didn't. With only 8 focus students this year, we experienced a massive lack of manpower, of course. And delays in the manufacturing due to the high demand this year were not helping either. And finally, we are still just students who make mistakes and thus generate even more delays. But it's exactly these mistakes which help us grow into better engineers. So, to sum it up, we had to compensate the delays by pushing back the testing phase. But the project is not over yet. We are still working day and night to finalize Bernina, go to the competitions, and win some races. Working is such a passionate team where the dedication is so high is truly rewarding. I'm proud to be a part of AMZ, and I want to say thank you to every AMZ member who has put effort in this year's project. Also, I want to thank all the alumni who gave a lot of inputs and who were always there to help when it's most needed. Last but not least, I want to thank all the sponsors who supported us in this very challenging year. So yeah, now we'll show you the making of bernina. Enjoy. Yeah, whatever. Ladies and gentlemen, we will now present you our 15th prototype race car, bernina. Please enjoy.
So, good evening also from my side. I'm Alessandro. I'm part of the software team, and I'm really happy that you could finally see our new car in all its beauty and the little demonstration of our active aerodynamics. And I want to thank Ilya and Goranj for showing us the manufacturing process, which, as you have heard, was not easy this year. But actually, the challenges started even before the manufacturing, in the design phase, because this is the first year that we're building just one car, designed from day zero to be driven both manually and autonomously. So we had a few challenges to overtake, and critical factors were weight efficiency, because a manually driven car cannot be fast if it is not light. And so we had to reduce our setup, both from sensor and computation point of view, and also think about the positioning of our hardware, because we had to take into consideration the human driver. So I will give now the word to my teammate Manolis, which will walk you through the first sense of the car, which is vision.
Hello, everyone. My name is Manolis, and I'm perception engineer at AMZ. I will start by talking a bit about the way that bernina perceives the environment visually. So essentially, I will start by talking a bit about the eyes of bernina. As Alessandro mentioned, one of the main challenges we faced this year was to minimize the overall weight of our car. As you can see on the slide, that is our old car Pilatus, and the perception setup was comprised of 2 LiDARs and 3 cameras, totaling 5 sensors. This year, we moved to bernina, and we decided to change this setup and just put 1 LiDAR and 1 camera, minimizing the overall setup. This led to 3 less sensors, which at the same time reduced the overall weight of our sensor setup by 50%, going from 3.8 kilos to just 1.9 kilos. At the same time, this reduction of the sensors also reduced the power rating of our perception setup by, again, almost 50%, accurately speaking, 47%. At the same time, because we reduced our total cameras from 3 to just 1, we also reduced the data that we had to process. So from just 14.7 megabytes per image frame, we went by changing to just 1 camera and at the same time cropping our image to 2.7 megabytes per frame, totaling a reduction of 82%. However, nothing comes for free. So in order to have all these improvements, we had to reduce also the overall field of view of our camera, which was reduced by 22%. This we tried to tackle by changing the overall architecture of our perception pipeline, which you will see just now. So let me talk to you a bit about the problem that we had to face in perception. What we try to do is essentially predict cones as accurate as possible. And the way that we do that is shown on this slide at a very high level. So as you can see at the left-hand side of this slide, we have the two sensors that we use, which is the camera and our LiDAR. The first step that we do, that you can see at the left-hand side, is to process the point cloud that we have, to essentially remove the unnecessary parts of the point cloud, such as the ground and the general environment. As soon as we process the point cloud, then we move to the sequential sensor fusion block of this block diagram, which essentially fuses the two sensors, the data from the two sensors together. For this, we use a neural network for our camera, which at the same time we combine with certain sensor fusion heuristic filters in order to optimally combine the two types of data. However, we have a constraint there, which is the field of view, as I mentioned before. More specifically, we have just 105 degrees field of view from both sensors. So in order to improve that, we decided to use another important building block by just detecting the cones from the LiDAR and do another clever step of fusing in a later fashion the two detections in order to get to our final output, which is the color position, the cone position, the colors, and all the probabilities. Next, here you can see a video of our old car Pilatus with this pipeline that I just described. At the top, you see the actual view of the car with the point cloud overlaid on top, and you can see in green the points from the point cloud that we actually use. This picture is then transformed into world, as you can see at the bottom of this video, which is essentially what Bernina, our car, will understand that the world will look like. And now that you have an idea of how we see the environment, I will give the word back to Alessandro to describe to you the rest of the predictions, the estimations that we need to make.
So bernina does not only have eyes, it also has spatial and body awareness. And we achieve that with a broad set of sensors that we put on the car. First two are the INS and the IMU, so the inertial navigation sensor and the inertial measurement unit. Through this, we get acceleration and yaw rate, and we also synchronize the sensors from a time point of view. Then we have the optical velocity sensors, which gives us accurate lateral and longitudinal velocity measurements. And finally, we have the steering actuator, from where we take the steering angle. All these sensors, together with the wheel speed, which we get from the wheel encoders, and the motor current, we feed into velocity estimation, which is the first step of our estimation pipeline. This block is very important because it gives us a very accurate estimate of the velocity we are at to pass to mapping, control, and grip estimation. Speaking about grip estimation, this is one highlight of this year. It was never done before in the history of AMZ, and allow us to run at the limit of the grip that the car has on the floor, on the ground. So it's all about tires, and as you can see, without grip estimation, we are hitting a lot of cones. So if you look at the left wheel, it's hitting 8 cones in total. But with grip estimation, we can run at the limit of grip without ever slipping on the ground, and we can achieve a much smoother run. Estimation is also about mapping, and we achieve that through our SLAM package, which stands for Simultaneous Localization and Mapping. This gives us a global map of the track and localizes the car inside it so that we know where we are. And an important part of the SLAM pipeline this year, since we are dealing with two kinds of different output from perception, so the colored cones and the uncolored ones, is to actually do data association and match these two. So when the cones are seen by the main pipeline, they get the color they have. And these colored cones are then passed through boundary estimation, which is pretty self-explanatory. It estimates the boundaries of the track, so the left and the right one, and also the midline between them. And this is done by color-based heuristics, as I said. And the goal of this package is to achieve the longest possible estimate of these boundaries and midpath to pass to control. And you can see that clearly in this video. So before we start, you can see that we have both white dots and colored dots. This is because we are mapping both the LiDAR cones without color and the ones with color. And as we start, the SLAM package, the localization package, maps all the cones. And as you can see, at some points, we have the full map with all colored cones with the right color. And boundary estimation can achieve its midline the longest way possible. So you've seen how do we estimate the map and the path, but now we need to control the car. And I will give back to Manolis to talk about control.
Yes, so now that we have seen the environment around us and we have built our map, we need to think of how we move on. And that happens in the brain of bernina. The brain of bernina actually consists of two main parts. First, it's our custom-made computer box, which you can see on this slide. And this year, we made some changes in the computer box. First of all, we integrated a new, lighter GPU in order to reduce the overall power consumption of our computer box. This was successfully reduced by 145 watts. And at the same time, a new addition of this year was moving from a water cooling system that was previously used in our cars into a new, again, custom-made air cooling concept that you can see in front of this image. The second part of our brain, the brain of bernina, is called the electronic control unit. This is a fast computer which essentially controls all of the electronics of the car, and at the same time performs some key operations, such as traction control, torque vectoring, and at the same time estimates the velocity of the car that we need. So now we thought, and we did the thinking process, we need to actually act, and that's where control comes in place. At AMZ, the overall architecture of our control pipeline is split into two main parts. First, we have high-level control, or HLC, which uses model predictive controllers, essentially a numerical optimization type of controller, in order to actually produce the optimal path that we want the car to follow. As soon as the optimal path is there, which you can see at red, then we move on to the second part of our control pipeline, which is the low-level control, or LLC. For this, we use a combination of PID controllers and feed-forward controllers, which essentially are used to track this path as fast as possible. The benefits of such a combined architecture is that we can achieve elaborate motion planning through the use of model predictive controllers, while at the same time achieve a high-frequency tracking of our path, and at the same time, high-frequency traction control and torque vectoring. This leads to a fast reaction to our velocity estimation and brings us to the main improvements of control for this year, which I will highlight next. So first, we changed the model that we used for our car. Last year, we were using a two-wheel model, and this year, we decided to model our car more precisely by moving to a four-wheel car model and by independently controlling each wheel. At the same time, we integrated, as Alessandro mentioned before, grip estimation feedback into our control loop. This overall will manage to minimize the overall model mismatch and make our model be as close as to the dynamics of the real car. Last but not least, as soon as we moved to a more precise but complicated model, we also needed to change the way that we solve our optimization problem. And for this, we decided to change the solving method and moving into a so-called SQP method. So with this, we can move on, and we can see the controller demonstrated live. Again, at the top, you can see the view of the car through the camera, and at the bottom, you see the actual path that it's generated and is followed by the car. At the right-hand side, you see the overall speed of the car and also the length of the generated trajectory that we want to follow. And now that you have seen the whole pipeline, let's move back to Alessandro for some closing statements.
So you now know about our full pipeline. But what are the goals we developed it for? So this year, the goals were two. So keeping the high performance we have always achieved, but at the same time, improving reliability of our algorithms. And we have some tools we use for that. So first is key performance indicators. Those are metrics and graphs that we use to evaluate what we implement. And we also check those automatically in our continuous integration. And as soon as the checks are completed, we can move to simulation. As you have seen, we can simulate the full pipeline in order to understand if the features we are developing are going in the right way, and we are just making improvements and not going back. And of course, after simulating, we want to see it on the real car, so we go testing. And you will have an overview of this in the auto show after. Thank you very much for your attention.
Thank you. A big thanks to Ilya, Garange, Alessandro, and Manolis for introducing us to Bernina. I can't wait to see our newest race car hitting the tracks all over Europe to show if the newly developed concepts will bring the decisive advantage. For the team, I am personally so proud of what they have accomplished. Looking a few months back, their learning really is put into perspective. A technical problems, 5 minutes later, a bunch of solutions is already discussed and evaluated. Everyone knows what to do to reach that common goal of getting Bernina ready to race, how to communicate efficiently, or how to organize oneself. And then I want to come back to something that is especially important for a project like ours. It is the support from all our sponsors and partners that enables a project like this. They mill, they turn, they print, they paint for us. They provide vital financial resources and help us out with questions, motivate us with events, and invite us to exhibitions and keynotes so that we can show to the grand public what we do. Let's give a big applause to them. And with this, I will let you enjoy our next video already.
AMZ in 3 words for me is team, perspective, and growth.
AMZ in 3 words for me is passion, creativity, and team spirit.
Dedication, passion, and privilege.
It's very, very challenging, but at the same time very exciting, and you learn really a lot.
My name is Karan Tiwari, and I'm part of the inverter module. If I would have to describe AMZ in 3 words, I would choose unique, challenging, and exciting.
Team, effort, and success. Because we would not be doing any of this if we weren't a team, and there is a lot of effort involved in order to success.
As last part of our presentation today, we want to thank a very special person to us, to AMZ as a whole. Herefore, I welcome on the stage Matthias and Johannes from the board.
Thank you, Jan, and good evening, everyone. On this picture, you can see the team of 2019 somewhere in the Swiss Alps where we spent a weekend together. While some of the students of our association spent multiple years with us, someone clearly was with us for the longest time. On the left, you can see our longtime supervisor, Dr. Jörg Heingärtner. He started supervising the first bachelor's thesis in 2009 and became the official project supervisor from ETH in 2010 and stayed for the upcoming 12 years. In this time, there were over 200 students in terms of a focus project, bachelor thesis, or semester project that he supervised. Dear Jörg, in the name of the whole association and the over 200 students of the past 12 years, we would like to thank you today for your continuous support. We wish you all the best for your future and for your new job, and we hope we can welcome you again in the future at another event or rollout of AMZ. I ask for a big applause. Thank you.
Also ich möchte mich auch noch kurz bei den ganzen Studenten bedanken hier. Es war mir immer eine große Freude, mit den Studenten zusammenzuarbeiten und zu sehen, wie aus jungen Leuten ein Team wird, Ingenieure werden, die ein gemeinsames Ziel verfolgen. Und es hat mir immer sehr viel Freude gemacht, sehr viel Spaß. Und ich wünsche euch auch für die Zukunft viel Erfolg, viel Glück und ruhiges Fahrwasser vor allem auch. Danke.
This is already it for our presentation in here. For the people in here, on site, we'll continue outside with a show run. Therefore, I invite you to move outside. You see there's a banner on the right side. Please stand to the right side of that banner, so next to the street, so you have some distance to the track for safety reasons. You can make your way slowly, grab still something to drink and eat on the way. We'll meet you outside. For the people on the live stream, we haven't forgotten about you. There's the Q&A following right now, so tune in, scan the QR code here, and ask all the questions you have about us, our car, us as an association. Thanks a lot.
On attend un petit peu. Let's get the stand.
Non, pas quoi.
Hein?
Tu le prends une fois?
Une fois? It worked? I don't know. Fuck. Hello? Yes. Okay, so for everyone on the live stream, let's go. So as the public is entering the view of Bernina, I hope you can hear me correctly. We'll continue with the Q&A session.
Entschuldigung, ich muss kurz auf die Seite gehen für die Kamera. Yes.
Come in the middle.
Come in the middle. You go to the middle.
You ask me.
Yeah, so we have a first question. The question is, Victor, what's the story behind the name Bernina?
So actually, the names of our cars having a very distinctive meanings, because since we're in Switzerland, and most of our country is, let's say, mountains and passes, we want to actually represent very proud of this being in Switzerland. And actually, the first 10 cars were mountain passes. Up until Gotthard, we stopped it and switched to mountain summits. And actually, the nice coincidence is that bernina is actually one of our sponsors, but it was not known before the vote. Right? Since every year the team is voting for the name of the car, and this year it was bernina, which is a summit in Switzerland.
Nice. And okay. Let's pick another question.
Finished? Okay.
Maybe for you, Philip.
I thought we do a break.
What?
We do a break. They haven't turned on the mics.
Okay.
So I guess we can continue with the question and answers. Oh, small technical problem. The beauty of the live.
Terrific.
Okay, so I guess now it's working better. We can continue with the Q&A.
Perfect.
Do you have a mic?
We go? Yeah, right.
Okay.
Okay, maybe a question for you, Philip. So what's the amount of hours that took for you for the project, for the whole project?
For me personally, for the team.
For you, for the team.
So
can we even count?
I don't think we can count that one, right? So as the focus students described during the presentation, like it's like each day of the week, 7 days a week. Even their phone thinks they're living in the workshop, like their home location is the workshop. So yeah, it's like endless hours of hard work, of passion. But yeah, I imagine each of the team members and each from our student team knows how much work goes into such a race car. So yeah, as said, like it's really 7 hours, definitely more than 12 hours a day. But yeah, at the end, once you see the car, it definitely pays off. So.
And as we say, when we like, we don't count.
Exactly, that's the right motto, yeah.
So Victor,
yes.
Question for you.
I'm ready.
What was the biggest challenge of the project so far?
So definitely, I would say that the biggest challenge was like the innovation of this year, which is merging an autonomous race car into a car which can be driven by a pilot, which is a novelty from the rules, and which is completely new for us. And it comes with a lot of challenges, such as implementing the sensors, as we've seen in the presentation, inside a car which was originally designed to be driven by a pilot. And so this fusion is very new for us, and which had to be new challenge for us. What was also a new challenge for us was a reduced team, but in the end, as we can see the final results, it seems that, as Philip said, the hard work paid off, and it is.
I think, yeah, we can definitely elaborate on the question. Like, Ante, what's the hardest thing you faced this season?
Oh my God,
point of view?
That's a very difficult question. I would say that
working with such colleagues like this.
Exactly. So I would say that for the software team, the most difficult challenge is to integrate with the hardware team for the first time in the same year. Obviously, we had no alumni with experience in this integration, so we had to improvise a bit and make our own timelines. But yeah, this is working quite good so far. So we kind of changed the whole old car into the new car. So we changed the computer, we changed the sensor setup, we changed the software, obviously, so slowly the old car is becoming the new car up until now, when the new car is ready, and now we're ready to bring the software in the new car.
Yeah, like definitely, I would definitely agree. Like once you look at the car, it's the merge. It's definitely the biggest challenge for this season. Of course, there was also like some limitations on the hardware side, which were affected by the corona and the post effects of the corona season. But definitely, the merge of the car.
Right.
It's the thing that affected us the most, but actually, in my opinion, brings the biggest value to the association, because now, hardware and software are merged to one team. It's like super international team. Yeah, and I think each team member enjoys it quite a lot. So has some challenges, but
Definitely.
at the same time, definitely huge advantages.
I would have a question for you to continue with you, Philip.
Yeah.
Since you have the Chief Technical Officer, you might know everything on the car and how the parts actually, how are they manufactured. So I see that there are very complex cars, but I see a lot of self-laminated parts actually. Could you tell us a bit more about which parts are manufactured from the students and could you elaborate a bit on this?
Definitely, yeah. I used saw before the car. So like 99%, which is black, is out of carbon fiber. So already all that parts go into the work of the students themselves. Like they start from scratch, from designing the parts until making half of the molds. Going through the whole laminating process, the autoclaving process, processing all the parts. So that's definitely quite a lot of work that goes on that side already into the project, which students will do. On the other side, though, we also have the electronics, and there, for example, all the pick and placement of the electronic components, like the PCBs and so on, the wire harness crimping, all of that work is done actually by the team, by the students. But yeah, at the end, also a big part on our car, especially with the hydraulic decoupled suspension, are all the metallic parts, and those come back to our sponsors. We are actually really proud to relying on that cooperation since many, many years. So it's quite a good trade-off between professional manufacturing and the professional manufacturing of our students for composite materials and electronics.
Okay, thanks a lot for this answer. I would have a question for you, Antonio. Since AMZ is very well known for its software and autonomous system, so I would have a specific question on the MPC, so Model Predictive Control. And actually, could you tell us a bit more on it, and would you recommend it, or like, would it be possible as a first-year driverless team? So like, imagine a team which would eventually already have a car, would like to switch or to pass by the new regulation of the FSG competition.
Yeah, definitely. So this is actually a question that got asked many times to me, especially during IWO. So this event in Hamburg that we joined a couple of months ago, and really recommended to every Formula student team. So I would, so if the team is like first year, I would not recommend to go to MPC like directly. I mean, it's quite involved, and to get it to run is really difficult. Okay. So first, I would suggest, get the car to drive the first time, and maybe use a PID controller for the forward, so the longitudinal dynamics, and for the lateral, maybe a pure pursuit. This is what AMZ did in the beginning, and it worked quite well. Also, I know of teams that perform really well, and they still use this setup. MPC is suggested once you get this setup to run. So you can try for the first time, maybe with the Cartesian coordinate, and then move to curvilinear bicycle model first, and then maybe, as we did this year, move to four-wheel.
Okay, thank you. Now I would like to continue with a question for Philip.
Yeah.
So as everybody knows, AMZ is known for its world record for the 0 to 100 kilometer per hour in 1.513 seconds, which is for now unbeaten since 2016. But do you think it would be possible with for instance, our new prototype bernina to beat new world records? So for instance, combining the autonomous system in order to further improve the performance, or what would you think of this? Would it be possible? Would it require too much work?
Yeah, like I would say, like from a hardware point of view, the car is for this season like just the bare car is obviously heavier due to the autonomous components, but now taking into account the fact that we actually wouldn't need any driver for making this acceleration run from 0 to 100 kilometers per hour.
We would save 30% of the weight.
Exactly, so it's quite important.
Advantage.
Yeah, exactly. And if you now look back at FSG, for example, from previous years, I mean, like the software team already proved that they could beat the electric team in acceleration run. So yeah, I would say
acceleration is the force divided by the mass.
Exactly. So yeah, I would say having the car ready, if everything is set up, we have the most powerful motors so far in AMZ history. So yeah. If we get challenged, we might take again the chance to create a new world record, let's say.
Are you challenging other teams? Okay.
But I was now mentioning software in the past, so Antonio, I think you can elaborate a bit on your perspective. What do you think? from a software point of view, is it possible to beat the world records?
Well, work record acceleration, obviously. I mean,
Okay,
I would say
it's a bold statement.
in the sense
Okay.
you don't need much, complexity to do that. You just have 70 kilos less.
Yeah.
The challenge is the human driver on like an autocross track. That's really difficult. And I mean, honestly, we're still not there because I mean the controller making the controller drive on like when the car is sleeping really a lot. It's quite difficult, and we're not there yet. We're close, but
maybe this season
there's some work to do.
I mean, this is
maybe.
We have two definitely really cool tools for that, like the grip estimation.
Definitely.
So
we are working towards this goal, definitely.
Exactly.
Okay, we have an operation question. Yeah,
ready?
So, the public is curious to know how many people are in our team, and why did we choose this number of people?
Okay, so this year we are a team of approximately, I would say, 80, considering the people from last year, which are giving advices. And so basically, there is a core team of 8 focus students from the ATH Zurich and 4 from the ISLU from Luzern, plus around 15 core members in the software team. So this is really our core team, which is basically working all the time. So they're living in the workshop. And then on top of it, in order to support them, there can be students in second or third year, or even master students who would be doing projects or basically learning the team, and they are around, I would say, 30%. On top of this, there is 5 team lead, and I have 2 with me, and a team of approximately 10 module leads, which are responsible for the modules, so for instance, chassis or aero, and in weekly meetings, they can make sure that the car goes in the right direction.
Right. I'll get a question that I'm going to reply myself.
Okay.
If you allow. So the question is there any chance to get into the driverless team as a bachelor student? Maybe you can hold this now. So usually we get master students for the driverless team as core members. There's not a rule, but it's more like something we do. But definitely, like bachelor students can help as freelancers in the team and have a small project that I mean they can help with. Now we'll go to the live demo. We thank you for your attention, and yeah, thank you very much. Enjoy.
Thank you very much.